This is where we start our practical module about the Navier-Stokes equations. And I encourage you to do steps 1 through 4 by the end of this week. So, first step. First step is going to be one-dimensional linear convection. So this is the ultimate simplification of some of the physics that are obtained in the Navier-Stokes equation. The 1D linear convection. So this, in 1D, we have a partial derivative of u with respect to time. We don't say what u is. It doesn't really matter. It's just a quantity that is transported with a flow that has a constant velocity c. Okay, so we've removed the nonlinearity. There's a constant. There's then a constant transport velocity c. So what happens with this equation, what the physical behavior of this equation is that an arbitrary initial profile, if you have any arbitrary initial profile, u0, no, let me write it, u of x at times equals 0, which now I'm going to just call u0 of x. Any arbitrary initial profile simply gets transported with velocity c, so after time t, then the quantity u of x is just the initial profile, but displaced with distance by a distance x equals ct. That's all. That's all that happens. That's all that should happen, right, with this equation. So the solution, therefore, the solution is given by u of x comma t is equal to simply u0, the initial profile, but displaced accordingly to the point in time that we're looking at. So this equation can also be seen as a wave propagation equation. With the interpretation of u as a wave amplitude having a phase propagation speed c. And so there is this relationship between pure convection and wave propagation, excuse me, that is an equivalence that is critical to the understanding of the physics of convection. So now you know what the equation must do and what should happen, right, in the physics. So let's look at now the discretization of this equation with finite differences. Well, it's not that hard. We're going to consider a space-time discretization. We're going to consider an index I, which is the index of the grid in X, and we're going to use an index n for time, and the numerical scheme that we're going to use so here we have our steps of CFD. The first step is discretization. Of this discretization has two components. One is dividing space, and we're telling you how it's going to be. And the second step is to discretize the equations themselves, for which we use a numerical scheme. In this case, what we're going to use is forward difference in time and backward difference in space. So we can write a discrete equation using this numerical scheme And the forward difference in time allows us to approximate the partial derivative with respect to time. Forward difference. So remember, n is the index on time t. So we look at a point I, a specific value of x, and we're going to look at two different times. It's forward in time. So we're looking at n plus 1. We're going forward in time. So let's estimate our derivative using that concept. We have u at point I, but time n plus 1, minus u at point I, but time n, divided by delta t. Here we have our first order approximation of the time derivative. It can't be simpler. Okay, now we have c, that is a constant, no problem, and we have a backward difference in space to approximate our spatial derivative here. So it's backward difference, therefore the time is going to be constant, so n applies, but the point is going to be I and I minus 1 because it's backwards. So we have u time n, that's constant, and we have point I minus u at time n, which doesn't move, and then point I minus 1, and divided by delta x. And here is our approximation to the partial derivative with respect to x. Again, it can't be simpler. All of this is equal to 0. So now we notice that, in fact, we have only, if we have an initial condition given to us, so we have this arbitrary profile that I said before was available to us at time equal to 0, then we can have that value known. If n is equal to 0, we can have all of these value knowns, and we can get the next time step n plus 1. And once we get n plus 1 for every single point I, then we're going to have these guys, and we're going to go to n plus 2. That's why this is called time marching. It's going to be a time marching calculation. So what we need to do is isolate this only unknown for a given step in time. There's only one unknown, so we transpose. We transpose the equation to obtain the variables, the values of the function u at time n plus 1 from the values at time n, and that is again very simple. We just write, you can see very simple here, u I n plus 1, and I can just move everything to the other side. It's going to be equal to u I n plus c, and I've multiplied over by delta t to isolate this guy, so c times delta t divided by delta x, and I have u I n minus u I minus 1 n. So you see, we have now everything. Yes, here. Yes. Thank you. Thanks very much. This is the equation that gives us the values at a forward moment in time as a function of a previous time. So in my PDF that you'll see online, there's also that very mistake. I'll try to correct it. And so this is going to be the assignment. This is what you need to program. And the next thing that we need is an initial condition, an arbitrary initial profile, of course, to be able to advance this in time. So we consider as initial condition, we're going to write this a lot of times, and so I'm going to abbreviate initial condition. That's going to be u equal to 2, constant value 2, at the interval between 0.5 and 1 for the value for the independent variable x, and u is equal to 1 at, well, everywhere else we're just going to consider the domain 0, 2. And we also need a boundary condition. The boundary condition is going to be u is equal to 0 at the edges of this domain, which is x equal 0, and 2. So basically this is what we call, this initial condition, this is what we call a square wave. Okay, what it looks like is very simple. It just simply looks like it's going like that. Its value is equal to 1 there, and then it goes to 2, and then it takes the value 1. And then at 2 is 0 again. And this is 1, and this is not drawn to scale, more or less. Okay? That's it. It's just a square wave. That is your square wave, your initial condition. Alright? This is the formula. This is the initial condition. You can now write a program to solve the one-dimensional linear convection equation, and I'm going to give you a pseudocode for that. This is really kind of like Matlab syntax, but it's kind of like a pseudocode, okay? So it's just, so what is this? A simple program that does this. We define in this simple program, we've chosen to divide the domain in X in 20 points. So the number of points in X, this is just a variable that I choose to be equal to 20, could be anything. I've decided that I'm going to do the number of time steps that I'm going to do are going to be 50. So these, I'm just here defining my initialization for the program, my initial variables. I've decided that my step in time, delta t, is going to be 0.01, and I've decided that c is going to be equal to 1. So once I have those, I can calculate delta x from the number of points in X, and of course the domain is from 0 to 2. And so very simply, I say delta x, I can calculate that. So now we have all of our variables to initialize the program. And then we want to have establish our initial condition. Here we establish the initial condition, which is the value of u for every one of those points here that I've defined to be these 20 points that go all the way to 2. These are 20 points. Okay, so for all of these points here, we're going to define the value of the function u, and it's very simple, between 0.5 and 1, that is equal to 2. Everywhere else is equal to 1. That's our initial condition. So here we have the initial condition. Okay? Then we actually advance in time, and we use, now this is the actual, there's a for loop in here, which is nested, because we calculate for every point within each time step. So for time step 1, we calculate all the points. For time step 2, we calculate all the points. And that's why we have a nested loop right here. So for the first time step, we go here and we establish that our variable at that time this is just an auxiliary variable, is equal to u, that is calculated here, and then we go in here and we are applying this equation, the finite difference equation right here, where we have, of course, at the time that I'm calculating, then the auxiliary variable that enters here, and then I have minus c delta t divided by delta x, and I have the difference right here. So this is just a very simple program to do that. And your assignment for step 1 is simply to do that very same thing in Python. Simple as can be. Right? Everybody happy with that? Any questions? Okay. That is step 1. Step 2 is 1D convection. So the only difference with the previous case is you will notice that now we don't have C, we have U there. So by multiplying U with du dx, we have a nonlinear term. The only difference with the previous case is that we have added the nonlinearity, which is present in the Navier-Stokes equations and corresponds to the physics that we want to eventually be able to model. So this is actually called also the implicit Burger's equation. And this equation has the property that it can generate discontinuous solutions from initial conditions that are smooth. It can generate well, something similar to shocks, okay? So this is the interesting part of the physics, which is, of course, present also in the Navier-Stokes equations, is that this equation can generate shocks. From smooth initial conditions, similar to shock creation. For supersonic flows. So, we discretize just like in step 1, and so we have our approximation for the partial differential derivative with respect to time is going to be, we're going to use forward difference, which is also called, by the way, the forward Euler method. We already said Euler is the guy that came up with this. It's called the Euler method for obvious reasons. So we go and write this forward in time, u at the next time step, which is n plus 1 at a particular point I, minus u at time n divided by delta t, and plus, the only difference, we don't have c here anymore, now we have u. So we have u at time n point I multiplied by u, we're going to use backward difference, so it's u n I minus u n I minus 1 divided by delta x is equal to 0. So again, just like in step 1, we transpose this equation to get the only unknown at n plus 1 in terms of all the knowns. So we can write u n plus 1 is equal to, and let's not make the same mistake as before, and I have a minus sign then here, and it's ui n times are multiplied over by delta t, and I also have this delta x over here, and it's, oh, no, I don't have a division anymore, I just can put the parentheses here, u n I minus u n I minus 1. There. That's our equation. So we're going to use as initial condition u equal to 2 at the range between 0.5 and 1, and u equal to 1 everywhere else in 0.2, 0,2, basically the same as in step 1. And the boundary conditions are u is equal to 0 at x equal to 0 and 2. And you can see that we have a very similar situation. Basically, the pseudocode is the same. We initialize a number of variables. Here I've chosen, and note that I've given you this just as a a choice of number of points and a choice of time steps and a choice of delta t. But part of your assignment is you code the same thing, but then try different values of those parameters and see what you observe. And of course, if you have a presentation afterwards, I don't want you to present exactly what I've just presented to you, because there's no point, right? You show me what you found, okay? The way we're going to do this is you're going to put your codes in Blackboard on the digital dropbook, so I can see that you've done your codes. You're allowed, of course, to collaborate and ask each other questions, but you need to do your own program. And then when you present, I want you to present your conclusions, not this, right? Okay, so for that reason, you want to try different values of this, of these parameters here. and see what happens. Okay? So here's our initialization. The only difference with the previous case is that we no longer have c as a parameter because c doesn't appear in the equation. We now have u. The initial condition is exactly the same. So basically, now you're going to see one of the first nice things that you want to do as a computational scientist, reuse your code. You're going to start do step 1, and to do step 2, you're going to reuse half of it. Okay? It's an incremental step. You're going to change only a little bit to get to step 2. The part that's different, of course, is here in this formula where we have used this difference scheme, and you see that instead of having C, the only difference is, of course, this guy over here, which before was a C, and now it's U of I and N. Okay? It couldn't be simpler. Do you agree? Steps, for the next 2 steps, steps 3 and 4, we're going to need approximations of the second order derivative, which we haven't seen yet. So let's just make sure that we know how to do that. So we want to approximate second order derivatives. Geometrically, the second order derivative is like the slope of the line tangent to the first order derivative. So if I calculate the first order derivative and I plot that, then the line tangent to that is going to be the second derivative, right? So because of that, so because of this geometrical interpretation, we can actually we can use approximations to the first order derivative. Let's just write u dx. It's quicker. At 2 locations to get the approximation to the second order. Second order derivative. For example, we can obtain a central difference approximation of second order by combine a forward difference and a backward difference for the first derivative So first, let's consider the whole Taylor expansion. And write ui plus 1 equal to ui. We've done this transposing that I was telling you before. Now on the Taylor expansion, just isolating the point I plus 1 is equal to ui plus delta x and the first derivative du dx at I plus delta x squared over 2 second derivative du dx at I plus delta x cubed divided by 3 factorial, which is 6 d3 du dx, and so on. Let's just write higher order terms. That's the forward difference. That gives rise to the forward difference approximation. We just dispersed 2 terms, but I'm writing the whole Taylor expansion. And let's look at the backward formula. ui minus 1 equals to ui, and then we're just going to have some alternating signs here on the odd terms, odd powers of delta x. So delta x du dx at I, this is plus delta x squared over 2 d squared u dx, and minus delta x cubed plus higher order terms. Okay, so now add together these guys. And of course this cancels out. All of the odd terms cancel out. And we obtain, and then we can isolate the second derivative. These guys cancel out and we can isolate the second derivative. And we write second derivative of u with respect to x at I is equal to u I plus 1 minus 2, so I'm taking these guys to the other side, minus 2 ui plus ui minus 1, so taking this one, 2 of these, and this one, divided by delta x squared. Well, but it seems like I've missed a 2. 2 delta x squares in my, oh no, it's okay. Because I added these 2 and so the 1/2 go away. And this cancels out, and the next term is going to be a term of order delta x to the 4th. And when I divide by delta x squared, I get order delta x squared. Do you agree with that? Everybody agree? Good. So here we have our central difference approximation for the second order derivative. Good. So now we can do our step 3. Do I have anything else here that I want to say? I got 2 different things that I'm following. Okay, we have our second order derivative. Now we can do our step 3. Step 3 is going to be pure diffusion. Just pure 1D diffusion. So this, well, this is what's called the heat equation, of course, or pure diffusion, heat equation, or Fourier equation, and applied to this, applied to the temperature, it's if U is equal to the temperature, this is the heat equation, and exact solutions are known for this equation for constant values of the diffusion parameter here. So if mu is constant, then we can get some exact solutions. My handwriting is getting a little bit messy. Okay, so for example, consider looking for a solution of type U equal to U hat, just a constant, e to the power I kx minus omega t, where I is the usual square root of minus 1, which represents a plane wave of amplitude, represents a wave of amplitude U hat, wave number k, and omega equals 2 pi f, with f the frequency. After introducing that on the PDE, we obtain the relation that I omega is equal to nu k squared, which leads to the solution U is equal to U hat e I kx e minus nu k squared t. So this represents the behavior of a wave in space with wave number k, which is exponentially damped in time with this term. We have exponential damping. exponentially damped in time due to the diffusion coefficient nu. So, well, note that the diffusion coefficient nu has to be positive for this to describe physical diffusion. If nu were less than 0, a negative value of the diffusion coefficient nu would represent an exponentially growing phenomenon. For example, an explosion. There are also some models that describe the flow of money from the concentration of wealth in the richer. It's like an opposite diffusion. The rich get richer. So there's a model for that. With the same equation, but the coefficient is negative. An economic model for the concentration of wealth. So pure diffusion, the important message of this is that pure diffusion represents an exponentially damped wave. So the physics of diffusion, and this is the important conclusion for us in terms of numerical discretization, the physics of diffusion is isotropic. It is isotropic in nature, and for that reason, the finite difference formula that represents best that type of physics is a central difference. You see now what I was saying in the beginning of this section, which is that the mathematical nature of the different physics, convection and diffusion, lead to specific numerical discretization schemes that are appropriate for that. This is a phenomenon that is isotropic in time, and the central difference is isotropic. It goes both ways, and it's going to be more appropriate for particular. It does not distinguish between upstream and downstream. Okay? So that's an important conclusion. Physics of diffusion is isotropic. So the finite difference approximation that is appropriate to this physical behavior is a central difference. Okay, so let's do now the discretization of step 3 for your assignment. You've got that down, the people who are taking notes? All right, so I'll clear that. And let's do our scheme. We're going to use a scheme. I explained why we are changing now our spatial scheme. The physics is different. So it's going to be forward difference in time and central difference in space. So discretize, as before. We have our time discretization as un plus 1 at point I minus un at point I divided by delta t. That is equal to nu, and we have our central difference that we've just derived, I plus 1 minus 2 ui n plus ui minus 1 n, and it's all divided by delta x squared. So again, we can isolate the future here in terms of the time n plus 1 can be calculated from the time n, and so we can write the transposed form to get u at n plus 1 is equal to UIN, and do I have a mistake again in my signs? Let me see. No, this time I don't. This time it's correct. Keep the plus sign here, the way the equation is written. So we have, oh no, I'm not going to write a fraction. I'm going to just write it as nu times delta t divided by delta x squared times uni plus 1 minus 2 uni plus uni minus 1. So we've got all that here. Here is our full then finite difference scheme for this equation. And you're going to do this with the same initial conditions and boundary conditions of steps 1 and 2. So, we have, as before, a part where we initialize some variables for our calculation, our numerical parameters, the number of steps in the x direction, the number of steps in the time variable, our delta t, our viscosity parameter, that wasn't here before, but the rest is the same. Here's our initialization. Here is our initial condition. It's the same as before, so you will have reused that part of your code here already for the third time. And here is our numerical scheme, where the differences are, of course, we have a viscosity here, we have delta x squared, before we only have delta x, and our central difference scheme, which is different than before. So you see here that your coding will only progress as you do the different steps. Okay, that is step number 3. Step number 4 is Burger's equation. So now we combine what we had in step 2 with what we have in step 3. We have pure convection with pure diffusion. We put them together. We have a convection diffusion problem. This is now Burger's equation. Oh, this shouldn't be there. It's just Burger's with an S. It's a very common mistake because the S belongs to the name, in fact. It's Mr. Burger's. Okay. Here's Burger's equation, and so, well, you see what's coming. You now have seen it a couple of times, so it's familiar, and we can actually almost write it by memory. Our forward difference in time, n plus 1 minus uin divided by delta t. Our backward difference in time for the first derivative in space, so plus uin, and we have un at I minus un at I minus 1 divided by delta x, and we have our central difference for the diffusion term, because diffusion is isotropic, and so it must go in every direction, in both directions in this case, because it's just a 1D problem. So nu, and we're going to write our central difference as un at I plus 1 minus 2 un in the middle, and plus un at I minus 1 divided by delta x squared. Here's our discretized equation, and now we want to rearrange the terms so that we can have a time marching formula where we isolate the only unknown, which is the value at time n plus 1, as a function of all the variables in the previous time. So we have uin, this guy, minus uin times delta t divided by delta x, and we have this uni minus uni minus 1, and there's our diffusion term now with a plus sign, nu delta t divided by delta x squared, and our second order difference, un I plus 1 minus 2 u n I plus u n I minus 1. So now we're going to have a little bit of a more elaborate initial condition. This is the initial condition that we're going to use. We were talking about Burger's equation, the 1D Burger's equation, which combines now the effects of both convection and diffusion. We wrote down the discretization of that. I don't think I need to write that again. And also the transposed form. And we had an initial condition that was the following. The initial condition, you might have it already, but let's write it again. The initial condition was u is equal to minus 2 nu. And here's a kind of auxiliary function phi that we're going to use. And we have d phi dx at the top, phi in the denominator plus 4. And this phi is equal to two exponentials, exponential of minus x squared over 4 nu plus the exponential of minus x minus 2 pi squared over 4 nu. So and the boundary condition is u0 equals u of 2 pi. So what we're imposing here is periodicity. So we can calculate this between 0 and 2 pi, and by assuming that the boundary condition here is always equal to here, basically this thing repeats over and over and over again. This is a periodic case, a periodic example. So this problem has an analytical solution, and so what I want you to do is when you plot your numerical result, so suppose this actually should look something like this, okay? It should look something like that, sharp, quite sharp. And so when you plot your numerical result, suppose that you have, I don't know how many points you might have, suppose you plot your points. This is, of course, not really part of it. If it was vertical, completely vertical, that would be just nothing. You might have just 1 point at the top, 1 point at the bottom. And plot your numerical value there with some sort of token marker or whatever, and also plot your analytical solution at the same time, so that you can compare immediately. And that's this is called, well, it's part of verification it verifies your, verify against the analytical solution. Okay, it helps to find bugs, and it also helps to recognize the types of errors that might appear in the numerical solution. So the analytical solution is again u equals minus 2 nu d phi dx over phi plus 4, but we have now for phi, and here, let me see, I've got it correctly, minus x minus 4t squared over 4 nu, and here's the t plus 1, plus x minus 4t minus 2 pi all squared divided by 4 nu t plus 1. So that's our analytical solution. And let me show you what the pseudocode looks like. Well, really, the pseudocode is kind of like just a MATLAB code with some added English words in between, but mostly MATLAB, because you all know MATLAB and it's quite readable as code. And, well, Python also is quite readable once you learn a few keywords, right? Okay, you got that? So, as before, we have our initialization of the code with a number of points in the x direction, or number of divisions in the x direction, a number of divisions in time, time step, the value of viscosity, and then we have the delta x, which is calculated from the number of steps in x. And then here we have created some auxiliary variables for our difference formulas, which are just I plus 1 and I minus 1. And we have here, again, this is just the initial point and the final point, and we have used them to, we're going to use this to establish the boundary conditions, the periodic boundary conditions. And so this is just the setup of the whole thing with our numerical parameters. And then if you have this in your script, you can start trying out different values here and seeing what happens. Then we have our initial condition. So you set your initial condition there as before. For the initial condition, we need a phi. Here is the d phi dx that appears in the formula. It's just exponential, so you can easily do that analytical derivative. So I didn't give it to you because it's just take the derivative of an exponential, so it should be easy enough. And it goes in here. And then u is obtained from d phi over phi, and that's the formula that you've seen in the previous slide. So here we got our setup of the calculation, our initial condition, and here we have the final calculation. So note here that we have to advance in time, and within each time step we have to go and traverse all of the points in the x direction. So we have some nested loops here. So here we're traversing on all the points in the x direction with our analytical solution so that we can plot that and compare. And here we are traversing our points in the x direction with our difference formula. And the blue here, the blue dashed line indicates the outside loop, right? These are the two inner loops to do our analytical solution and numerical formula, and an for every value of x, and an outside loop that does the time marching. Okay? So that you can see here, this corresponds to the formula that you have for the transposed form of ui n plus 1 in terms of un, and here's your delta t divided by delta x, and so on. And then you have the viscous term over here with your central difference formula right here. Okay, you recognize all that?